The topic is the synthetic reinforced structures. It's the same topic as Professor Watanabe explained, but I will emphasize the developments from walls to bridges. あれこれは動かない。
いやいや、動きます。これ、カーソルですね、右に持っていって。
これはなんだっけ
これで多分いくと思います。
違う、ポインター。
あ、このポインターオプション。
OK, sorry. これいいのかな ?OK. This is the abstract, the development and construction of various types of the synthetic reinforced structures, including those for high-speed railways for the last about 40 years is reported. In 1980s, GRS retaining walls with full height rigid facing was developed, for which after reinforced backfill and subsoil had deformed sufficiently, the full height facing is constructed, firmly connected to reinforcement layers. In the early 1990s, GRS Bridge Abutment that supports a simple girder at the crest of the full height facing was developed. About 170 have been constructed. In the early 2000s, GRS internal bridge was developed, for which the both ends of a continuous girder are integrated to the crest of pair of full height facing of GRS retaining wall. Besides, many of the embankments, retaining walls, and bridges that collapsed by earthquakes, floods, and tsunami were restored to GRS structures. The wall length of these GRS structures is now about 200 kilometers without any problematic case during and after construction, while very high cost effectiveness has been validated. First topic is a recent typical GRS structure for railways in Japan. So this is the network for Shinkansen. First is about this Hokkaido Shinkansen. Already Professor Watanabe showed this figure. The point is that all these GRS structures were constructed in place of conventional type structures. For example, here the A is a GRS bridge abutments. 33 were constructed. This is nearly 100% of the abutments constructed for this project. This is a cross view of the site. This is GRS box culvert. This is GRS retaining wall. This is GRS tunnel entrance exit protection. This is the GRS bridge abutment under construction. This was constructed in this way. First, a shallow ground improvement when necessary, then construction of GRS wall, and construction of full height rigid facing. The connection between the full height rigid facing and the backfill is very important. Then the placing bearing or shoe, and finally girder. This is a completed wall. For Kyushu, this will open this coming September. For this project, the GRS bridge abutment was constructed. 78 was constructed. This is 89% of the all bridge abutment. You can see in this project, GRS structures were constructed most densely for Shinkansen high-speed rail. In particular, many GRS bridge abutments were constructed, 78, in place of conventional abutments. This is the GRS walls at the Omura Depot. This is a view at the site. You can see here is a RC viaduct between tunnels. At the entrance of tunnel, there is a GRS Bridge Abutment here and here and here. So many bridge abutments were constructed in this project. This is showing how GRS Bridge Abutment were constructed. First, step one is bench cutting of stable natural slope. Step two is a construction of approach fill. The grid reinforced well compacted lightly cement mixed gravel. And step three is a compaction of the backfill, at least 95% of maximum dry density at the optimal water content by modified Proctor. I think this is answering to one question already made. And fourth is the arrangement of the grid layer. Fifth is the completed approach fill. And sixth is the completed GRS Bridge Abutment after construction of full height rigid facing. And here is a GRS tunnel entrance exit protection. And this is the details of this protection for tunnel. So compaction of the backfill and the arrangement of the zero grid layer. And this is showing an intermediate stage of construction of GRS walls on both sides of the tunnel. This is showing a GRS internal bridge. So first is the excavation of the subsoil, then the construction of approach fields. This is the grid reinforced, well-graded, well-compacted, lightly cement mixed gravel soil. So the grid must have a very strong, high resistance against high pH of the concrete. And third is the construction of full height ridged facing after the formation of backfill and subsoil has taken place sufficiently, then placing a PC girder, this is a cross-section in this case. Then finally, the structural integration of both ends of girder to full height ridged facing, then construction of a slab and others to complete the bridge. So this is the GRS internal bridge. This is GRS retaining wall, a side wall, a wing wall, and the tunnel protection. This is the view from another angle. This is GRS internal bridge, and so on. This is already shown. First of all, what I will show. This is the history of these technologies, and we have a number of big earthquakes, and this is the location of the project so far. Very important point that we have no problematic case during and after construction in all these projects. So no problem, zero problem case. So this is the GRS structure for North-South Commuter Railway, Manila, Philippines. So this is now under construction. This is one site. You can see here, this is a GRS internal bridge, and this is another bridge. And a number of GRS internal bridge are now under construction. This is the view view during construction in Philippines, and this is the cross section, and this is immediately before the construction of full height rigid facing. So this is a cost estimate for this project. When this cost for RC viaduct is 1, the cost for GRS retaining wall is of this value. When the depth of ground improvement is 0, then the cost becomes nearly half. With the increase in the depth of the improvement, the cost increases. Yet, for this 10-meter depth, still 80% of the cost for RC viaduct. Summary of the first part, GRS structure with full height ridge facing have become the standard railway structure in Japan. Most of them were constructed in place of conventional types of embankment, retaining wall, bridge abutment, and bridge system. A number of GRS structures were and are being constructed also in Vietnam, Indonesia, Philippines. This accomplishment is due to that. Compared with conventional types of structures, these DRS structures exhibit high performance under long-term ordinary conditions and against earthquakes, heavy prolonged rainfalls, floods, and tsunami, and lower cost for both for construction and long-term maintenance. Next, I'm going to explain the several theoretical and technical backgrounds for this DRS structure. I will explain these points. So this is already what I've explained, but I'll repeat because this is a very important point. Inextensive versus extensive reinforcement and flexible and stiff facing. So we have various types of mechanical stabilized earth retaining wall by flexible or stiff facing. Flexible facing, not developing high earth pressure on the facing, or stiff facing, developing high earth pressure on the facing, and inextensible reinforcement, typically metallic strips, or extensible reinforcement, typically polymer and planar grid. By different combination of these two components, there are different types of MSE walls. Type A, a metallic screen facing, and metallic strip. And this is a metallic strip and discrete panel facing. C is a wrap around facing and their grid. And D and E are, D is a modular block facing and the textile. E is a full height rigid facing and the textile. So previously many considered that the facing is only to prevent the spring out of backfill and to achieve small wall deformation and high wall stability. It is necessary to keep low earth pressure on the facing. So low earth pressure is better. So flexible facing, in this case, A and C is sufficient. However, we often observe that when using flexible facing A and C, the earth pressure on the facing is low, whereas wall deformation is large, sometimes too large, indicating the paramount importance of using stiff facing. So here, when facing is flexible, no earth pressure and low tensile force, that means low confined pressure and low stiffness and strength of backfill, so light deformation and low stability. So this is the first test embankment constructed long time ago. The facings wrap around. So we observe a large deformation. So this is flexible facing. To reach the equilibrium, we need a large deformation like this. So then on the other hand, we consistently observe that stiff facing like a modular block or concrete panel facing, this stiff facing that is firmly connected to reinforcement layers, and B and D and E, exhibit large earth pressure, which result in the small wall deformation and high wall stability. So this is another test embankment. We measured distribution of tensile force here. Here is a panel, a small panel, discrete panel facing. you can see we have a large tensile force at the connection. So wall was relatively stable, rather stable. So similar trends we observe in number of MSE retaining walls having stiff facing. So our goal is this high earth pressure and high connection strength, high connection forces, and high tensile forces, and high confined pressure, and high stiffness and strength of backfill, and small deformation. This is our target. So finally, we reached to minimize, previously many considered that to minimize wall deformation while ensuring high wall stability, the discrete panel facing or modular block facing is sufficient. But finally, we reached to this conclusion that full height rigid facing is important. So yes, very effective. So this is two test embankments and sand fill and clay fill. And here is a before construction of full height rigid facing, and this is after construction of full height rigid facing. So for this sand backfill, and two types of facing was used for 2 years. This discrete panel facing shows some deformation, but the full height rigid facing did not show displacement or deformation. And the loading test was performed. So the discrete panel facing showed that buckling like this. This is the cross section of this section. Here's a discrete panel facing, and here is a shear band. So this is a footing. So shear band reached to the facing at this point. Then discrete panel show the buckling here. So for other section F, G, discrete panel facing show the higher stability, and section D is length was reinforcement 2 meters, and F was length was facing was 1.5 meters. So D shows the largest stiffness and smallest displacement, but the stability of segment F and D was controlled by the yielding point here, yielding by controlled by yielding of construction joint, because this test embankment is a this concrete facing was not steel reinforced, no reinforcement. So actual full height rigid facing for all the prototype GRS retaining walls constructed subsequently are all lightly steel reinforced. So one more problem is this extensible metallic strips. Previously, many considered that for small wall deformation and high wall stability, it is necessary to use inextensive reinforcement such as metallic strips. However, there are two potential problems, corrosion and low pull-out strength. So I'll discuss this point. So the use of relatively short metallic strips can reduce the amount of excavation like this. However, they may exhibit pull-out failure. So this is another typical case of pull-out failure of metal strips, and this resulting in the local failure of facing the finally global failure. So the use of relatively long metallic strip is required to avoid pull-out failure of reinforcement, but it increases the amount of excavation, and while it may require the use of anchored sheet pile, so it increases the construction cost and construction period. So now we are using a GRS retaining wall with full height rigid facing. Here is a short reinforcement. Here, we can use short basic grid layers without losing a wall stability due to high pullout strength of planar geotextile, and by using several long grid layers and by using a flat ridge facing. This grid arrangement decreases the amount of excavation while not requiring use of anchor seat pile. So this is our current standard of practice. So later I will discuss more in detail about this point. So now a summary of this chart. The full height ridge facing firmly connected to reinforced layers can ensure small deformation and high stability of wall despite the use of relatively short so-called extensive reinforcement. So besides, full height ridge facing exhibits good durability and aesthetics. These points are discussed in the next section. So important point I like to emphasize that good compaction and good drainage of the backfill are imperative for good performance of GR retaining wall using full height ridge facing. But some insight in the function of full height ridge facing. So first of all, conventional retaining wall is a cantilever structure. So we have a large forces in the facing. So this requires a massive and strong facing. And we have a large overturning moment and large lateral thrust load at the facing base. So this results in the large stress concentration at the facing base. So we may have an unstable behavior, particularly against seismic loads. So we need a pile foundation. So this collapse of this type of cantilever wall during 1995 Kobe earthquake. This gravity type wall had been seismically designed using KH.2 with a safety factor 1.5. So this means design KH 0.55 is too low. This must be increased. And higher stability of wall is required. So GRS retaining wall with full height ridge facing is used for this objective. So GRS retaining wall is not cantilever structures. Along this potential active zone A, at each level, the active earth pressure is registered by the tensile forces, tensile reinforced layer, unlike a cantilever structure. And along the equilibrium, along the facing, we have another equilibrium B. So at each level, the earth pressure on the back of the facing is registered by a tensile force at the connection between the reinforcement and the facing, unlike a cantilever structure. So this is showing a paramount importance of high connection strength. So full height ridge facing of GRS retaining walls are continuous beam supported by many reinforcement layers at the small span, actually 30 centimeter. This is not cantilever structure. As a result, we have very small forces in the facing. So this results in a simple facing structure that is enough. And then small overturning moment and small lateral thrust load at the facing base. So we don't need a pile foundation. And generally stable even against seismic loads. But this is a typical comparison of the cantilever retaining wall. This constructed here some long time ago, and the new construction is by GRS retaining wall. So this is a complete wall. So this is a cantilever wall. We need a very massive piles. And with GRS retaining wall with full height facing, no piles, and very light facing. This is a picture of the GRS retaining wall with the flat facing taken 2 years before the earthquake. Earthquake was 3 years before. Anyway, this is immediately after 1990 earthquake. The wall survived. Yet a limited amount of, but noticeable shear deformation took place, about 2.7%. This due likely the use of a short geodetic cell like this, only a 2 meter long, that is 40% wall height per meter. This is a very unusual arrangement. So the question is, what is the necessary and sufficient length or stability? So this is an experiment performed by Professor Watanabe and other colleagues, and shaking table test. So simulating this model simulating gravity type. This model is simulating this GRS retaining wall having a short reinforcement. The test result is showing that the this is a gravity type. So displacement plotted against the seismic coefficient applied at the shaking table. And this is a GRS retaining wall with a short reinforcement. GRS retaining wall is better, but this is showing the 3 conventional type retaining wall, similar behavior. GRS retaining wall R1, this one is better, but R2 and R3 is better than R1. Finally, the R2, we finally selected this type because R2 is more stable than R1, while the similar behavior as R3. Whereas R2 is more cost effective than R3 because of first, the less amount of the grid here, and second is the less amount of excavation here. This is important when constructed on slope. So now R2 is recommended as a standard type in the current design code. So we have this issue to construct a retaining wall to widen the embankment crest. Often, this is very often case in urban areas. This is by conventional method. And this is MSE retaining wall with a long retaining wall. This is more cost effective than conventional retaining wall. But in both cases, these two walls, wall types require large slope excavation and the use of temporary anchored sheet pile. So which largely increases the construction cost and the period. So when the modular block facing, if the all short reinforcement is short, which do not fully cross the active failure plane, in this case, we have a shallow failure B. Then this resulting in a low stability against lateral sliding and overturning. Moreover, we have some damage to our unstable behavior or modular block. Then we may have this kind of local failure. So we use a long reinforcement, fully crossing the active failure plane A. So then we have a deep failure plane. So we have a high stability against lateral sliding overturning. But now we need a large amount of excavation and use of anchored sheet pile may be required. So on the other hand, reduction wall or wall stability by using short reinforcement is covered by first, the use of several long reinforcement layers extended to plane of reports, and the use of full height ridge facing. The 1 or 2, this arrangement facilitate the integrated behavior of an enlarged reinforcement zone. reducing the shear deformation and increasing the wall stability against overturning and lateral sliding caused by first backfill earth pressure, particularly seismic earth pressure, and the stability against against long concentrated external load here, vertical, horizontal, near the wall face. Typical case is construction of bridge girder. So anyway, so long reinforcement like this and fluid ridge facing is important to maintain high wall stability despite the use of basic short reinforcement. Then we have this situation, good stability and small excavation. So this is showing a zero grid length in the current design. The length of the basic zero textile layers is largest value among 35% of wall height for 1.5 meter, and the length required for a sufficient stability against overturning, lateral sliding, and shear deformation, evaluated by the Newmark method based on the two-wedge stability analysis. So this is a two-wedge stability analysis for general case. But when the with full height ridge facing, the failure plane always start point A, then the this contribute to the increase of stability. So three-dimensional effects, so already explained. So each wall section between two adjacent vertical construct joint, this is usually 10 to 20 meter length, behaves monolithically. So local failure will not take place, and facing can support local concentrated load VH, so we can construct the bridge. So another important issue is that the when this is the conventional retaining wall and earth viaduct. So disadvantage is costly, particularly by using pile foundation. But we have an advantage that is limited occupied space, and facing of retaining wall, this one can support other structures like a noise barrier and such electric poles and so on. The GRS retaining wall with facing of modular blocks or discrete panel. This is costly, but unlike conventional retaining walls and RC viaduct, a buffer zone is required to ensure the safe service of road and railway. So wider occupied space required, and facing cannot effectively support other structures. GRS retaining wall fluid ridge facing is less costly. Besides, like conventional retaining walls and RC viaduct, railway and road can be located very close to the wall face. So limited occupied space required, and facing can effectively support other structure like this. So this is a typical case. You can see the aerial track is very close to wall face. And this is another case here, the track located very close to the wall face and small amount of excavation. These are two important advantageous features of this wall system. Function of the full height ridge facing, summary. The facing is an important and essential structure component that confines the backfill, develops large tensile forces in reinforcement and support other structures. So the facing should be rigid enough during service. On the other hand, the facing should be flexible enough to accommodate deformation of backfill of supporting ground during wall construction. This is construction. So stage construction can solve the problem. So this is the advantage of stage construction of fluid facing. So this is one typical case before the stage start of construction. This is during construction, but before the construction of flow height is facing. And this is a completed wall after the construction of flow height facing. So this is a completed wall. This will construct in this way. Already Professor Watanabe explained start of construction and good compaction is important. 30 centimeter here. This is for also for good compaction. So a small lift, 15 centimeter, ensured by a small vertical spacing, 30 centimeter between grid layers. And here is no ridge facing existing during backfill compaction. So this is completed wall before the construction of flow facing, and this is the after construction of the flow facing. So this is explained already, and this is the field and laboratory test to evaluate separation test. Here's a piece of flow ridge facing cut from the actual facing, and this is a zero grade reinforcement, and this soil box filled with gravel. So this is cut from this part. So now this is lift up, so no separation here. And also a series of laboratory separation tests were performed. This is after test after separation. This is the separation strength and the separation displacement. So this is a equivalent force required to withstand the inertia of 2 meter thick facing under 1G. Actually, the thickness of 0.3 meter. So the separation strength is more than sufficient. So properties required to the grid: sufficiently high strength and stiffness with a low creep deformation. And second is high anchorage strength in concrete and backfill. The third is high long-term resistance against the high pH of concrete, because the textile is in contact with concrete, and good adhesiveness with concrete. So this is really 2 and 3 are important. Zero grid has indirect contact with concrete. Stage construction, last stage completed. So advantage of stage construction are explained. The completed wall exhibit very small residual displacement, differential settlement between flow height facing and backfill, and gravel backs protect the facing the grid connection. So facing the grid connection is hardly damaged during service. So construction of GRS retaining wall using a compressive backfill and on the compressive subsoil becomes possible. This is one case. Construction on very soft clay, so very difficult design and construction conditions, nearly saturated soft backfill, and very thick soft clay, and very long pile foundation, not realistic. So these problems were overcome by stage construction of GRS retaining wall without flow height ridge facing, then preloading fill, and settlement about 1 meter, and the removal of preload fill, then finally construction of flow height ridge facing. This is the view during preloading. So wall height was 3 meters before preloading. This became 2 meters after preloading. After removing preloading, construction of height facing, and this is a picture taken 20 years after construction. So this is working. So this several serious problems with the conventional method to construct a box culvert crossing road, railway embankments on soft soil. So we have, this is a construction embankment. Now we have a settlement. Then we have many problems: negative friction and the bumping and road concentration. So this problem can be solved by GRS box culvert. In this case, first we construct the GRS embankment, then settlement, then construction of GRS culvert, and then we have very small residual settlement. So the summary about the stage construction of flow hydraulic facing, and by stage construction, during wall construction, the facing is flexible enough to accommodate the deformation of backfill and supporting ground. And during long-term service, facing is rigid enough to achieve small deformation and high stability of complete wall. So this stage, okay. So next is GRS bridge abutment and GRS internal bridge. Rush, I have to rush. This is starting from conventional simple girder bridge to finally GRS internal bridge. So the conventional simple girder bridge, we have several problems. First, abutment and backfill. Now problem starts as pressure and settlement and lateral flow. And construction of bearing. So this is costly. And during earthquake, the wing wall could collapse, and so abutment may move, and simple girder will lose the stability. What is the solution? The first solution is the internal bridge. So internal bridge is constructed in this way. Backfill is the last. So this is very popular in the United Kingdom and the United States. However, we have several unsolved problems. One is these pressure problems and lateral flow and settlement problem. And the new problem is by this seasonal thermal expansion and contraction of the girder. By this movement, we have circulated displacement. Because of this, we have a settlement and increase in the pressure due to latchet mechanism. So this is the latchet mechanism, active displacement and the formation of active wedge. And the passive displacement, active wedge cannot recover its position. And then one more active displacement. This is the activation of the deformation of displacement active wedge. Passive deformation, the activation of the deformation of displacement of the passive wedge. So we have a active failure and increased earth pressure. So this is test results. So何分前だこれ。あと10分、15分大丈夫? Okay, test results by cyclic displacements. And here are the results and lateral displacement at the top. So earth pressure increased and settlement increased. So this is a very serious problem with conventional internal bridge using unreinforced backfill. So actually this is such an active failure takes place. So the technical solution is the GRS bridge abutment. Second stage is like this. We construct GRS wall, and flow hydraulic facing, and girder foundation. This is integrated to flow hydraulic facing, then bearings here, and simple girder. So reinforced zone here is to minimize the residual deformation, usually well compacted lightly cement mix and the reinforced well-graded gravel soils, particularly for high-speed railway. So the grid should have very high long-term resistance against high pH of concrete. Typically, we are using PVA. So yet this is very cost-effective, stable when compared to the conventional type bridge abutment and statically determinate. So not sensitive to long-term residual displacement of the flow hydraulic facing if it takes place. So rather simple and to design and construct. So this is a typical case. Is a bench cut of natural slope and during construction, the construction flow had rigid facing. So first one was constructed 2003, and this was 2012. After construction of the first one here, 2003, by 2022, nearly 170 have been constructed, including many for high-speed railways. These are all for high-speed railways. So simple girder bridge using girder bearings placed at the crest of a pair of GRS Bridge Abutment, second generation here. This is possible. A much better performance and cost effectiveness than the conventional simple girder bridge using girder bearings placed on the crest of a pair of conventional cantilever abutments. So this is simple to design and construct, so could be relevant to many cases. Yet, the following two problems remain. One, the high cost for construction and maintenance of bearing, and low seismic stability of the girders and the movable bearings. So GRS integral bridge, this is free from these two problems. Here's a combination of two technology, integral bridge and GRS bridge abutment. This is GRS integral bridge. So this is constructed in this way. So GRS retaining wall, flow height rigid facing, firm connection is essential, and continuous girder is arranged. Finally, structure integration. So we performed model tests to examine the performance of GRS integral bridge. So this is a cycle loading test here. So if the backfield is not reinforced, so by cyclic displacement at the top of the facing, we have a large settlement here. When the backfield reinforced but without connection here, still large settlement. Only with this GRS integral bridge, that means reinforced and good connection, nearly no settlement, no bump. A shaking table test we performed. So this is a model of GRS integral bridges. This is reinforcement. Some mass is pressed here to simulate long girder. So here the displacement at the top, and this is base acceleration. Conventional gravity type abutment show already large displacement at the top at the base acceleration of 200 centimeter per cubic second. So this also show GRS bridge abutment first generation show large displacement, and GRS integral bridge here, no reinforcement, show large displacement at the base. But GRS integral bridge show the large displacement only after large base acceleration by the rupture of the connection. So settlement here, these three conventional ones show large settlement, but the GRS integral bridge show near zero settlement, so no bump. So I skipped this part. So full scale model was constructed at the Railway Technical Research Institute, and lateral cycle loading tests were performed, simulating seismic loads and thermal effects. Then first one was constructed here for high-speed railway. This is the spine is 12 meters, it's short, but this is high-speed railway. You can see the very slender girder. And this one is a 3 GRS integral bridge for Sandy railways. This is the picture taken 20 days after 2001 Great East earthquake. So here was a simple girder bridges. Simple girder was washed away to inland by tsunami, great tsunami. So this then this bridge was restored to new bridge, and 3 candidates were compared. One is a conventional one, two simple girders. Second is a single continuous girder, but using bearings. Third one is GRS internal bridge without using bearings. Central pier is only to support vertically. And cost is lowest, seismic stability is the highest, anti-tsunami stability is the highest, and the need for maintenance work is the lowest. So this was selected. And this was the actual bridge, and this completed one, 40-meter span. This is another site. Here too, these bridges were washed away by great tsunami during 2001 great earthquake. So this is the completed one. The total span is about 60 meters, and you can see trains running without any long-term problem of maintenance. So the latest one is a two GRS internal bridge here, and for new high-speed railway, and this is GRS internal bridge, and this is GRS bridge abutment. And this is the view during construction. This is GRS internal bridge, and this is GRS bridge abutment. So in this case, some thin top layer was improved by in-place cement mixing to make the residual settlement minimum. And one point is we are using different shapes of reinforcement backfill zone. For GRS retaining wall, longer reinforcement at the top, and bridge abutment and the GRS integral bridge, longer reinforcement at the bottom. The reason is this: GRS retaining wall longer at the top. This is to minimize the excavation when constructed on slope, maintaining high wall stability by using several long reinforcement and full height ridge facing. And also, this is to stabilize this backfill immediately below the railway or road. And the negligible effects of differences in stiffness and radial settlement between reinforced zone and unreinforced zone, because the train is running in parallel to wall face. On the other hand, GRS integral bridges, this long reinforcement at the bottom, this is to ensure high stability against active and passive rotational moment about the facing base by seismic inertial forces of the girder and facing for more better stability. Second is avoid cracking in brittle cement mixing backfill if constructed on relatively soft deformable unreinforced backfill. And for a gradual increase from 0 to in the thickness of unreinforced backfill in the direction of normal to wall face to achieve gradual changes in the stiffness and the residual settlement in the backfill for smooth train vehicle running without bump. So, okay. So, but actually there are a variety of different variations like this, like this, like this. All depends on the ground conditions and other conditions. But anyway, all these arrangements are designed by stability analysis. Okay, so the summary of the GRS bridge abutment and GRS bridge were now standard bridge structure. Finally, collapse of soil structure by earthquake, flood, and tsunami, and restoration of GRS structures. Here's one case here. The collapse of the retaining wall during 1994 earthquake. this was restored to GRS retaining wall. Collapse here, you can see failure of the slope, damaged railway and highway. Railways here. And this was reconstructed. This is before the collapse, after the collapse, and this is restored to a GRS wall. And this is a view during reconstruction. And another site, failure, reconstruction, and so on. And we have many cases of collapse of railway by retaining wall by collapse, scarring. So overturning failure of retaining wall and collapse of embankment. With the GRS retaining wall, retaining wall, the behavior is much better. By scarring, even with the scarring, overturning failure may not take place, and the backfill will be safe. This is one typical case of overturning failure of seawall by scarring by storm wave, sea wave. This was reconstructed in this way. This is a view during reconstruction. Here before the construction of flood facing. This is during casting in place of concrete for flood facing. This is completely one. And this is the collapse of the wing wall for by flood. This is a large view. This is by scarring and collapse of wing wall. This is the reconstruction. Only 10 days to construct in this way. Finally, later, flood facing was constructed. Failure here. So this is a large-scale failure, 30 meters in height. So this is by scarring by river flood. This is the restored slope and facing retaining wall before the construction of flood facing. And this is completely one. Flood facing is very effective to prevent the failure of wall by scarring. So here is another case, collapse of RC viaduct by tsunami. This was restored to this GRS embankment. A summary, a number of conventional type embankments, retaining walls, and bridges collapsed by recent severe earthquakes, heavy rainfalls, floods, storm, and tsunami in Japan. Many of them were restored to GRS structures with flood facing because of their characteristic feature, including first, restoration, and second, high stability against natural disasters, even when constructed at topologically difficult sites, for example, slope, and low cost for construction and maintenance. The concluding remarks. Firstly, a number of GRS retaining walls have been constructed flood facing, GRS bridge abutment, etc., have been constructed as important permanent structure for a total wall length of about 200 kilometers, including those for high-speed railway Shinkansen. This accomplishment is due to high cost effectiveness by high performance during long-term service and against severe earthquake, heavy rainfall, and low cost for construction and maintenance. GRS bridge abutment, second generation like this, supports a simple girder with a fixed bearing at the top of the flood facing of GRS retaining wall. GRS bridge abutment is much more cost effective and much more stable than conventional type abutment. About 170 have been constructed. Since opening to service, all have performed very well with practically zero bumps. GRS bridge abutment is now one of the standard bridge abutments for railway in Japan. The GRS integral bridge structure integrate both ends of a continuous girder to top of the fluid facing a pair of GRS retaining walls, not using bearings. This is much more cost-effective and much more stable than the conventional girder bridge. GRS integral bridge is now one of the standard bridge system for railway in Japan. And many of the conventional type embankments, railway and bridge that collapsed by recent severe seismic loads, heavy rainfalls, floods, tsunami, etc., were restored to GRS structures having stage constructed fluid facing. So the last one, the following the three key breakthroughs for the development of the GRS structures explained in this presentation. First is the use of fluid ridge facing for changes from low earth pressure to high pressure at the facing, and from facing as a secondary non-structure component to facing as a primary structure component. Second, stage construction for the change in construction from facing before the backfill to facing after backfill, that is from backfill after facing to backfill before facing. Third is the structural integration of girder to fluid ridge facing with GRS internal bridge to change a statically determinate but unstable bridge structure to a statically indeterminate but stable structures. So thank you very much for my colleagues. And PhD file of the related technical papers of GRS structure by Tatsuoka et al. Can be downloaded from this home address. And this is a homepage of RR Association. You can find in homepage. Thank you very much for your kind attention.